So I am sorry I cannot be with you, but very glad to be with you virtually. This is the first of a series of 5 talks, so a mini course on how to compute with quantum walks. So here's a little bit of an overview. So I think if we're going to talk about computing with quantum walks, applying them to something, the first thing we should do is make sure we know what computing is. So that's what today's talk is going to be all about. Excuse me. And then tomorrow I will dive into the basics of how you compute with quantum walks, like things you can do, things you might want to do, maybe shouldn't do. And then we'll look at search algorithm, some aspects of it, and as a lead into using quantum walks for optimization problems. And then on Thursday specifically, we'll look at how quantum walks can find spin glass ground states. And on Friday, we'll look at a little bit of the aspects around using quantum walks in this setting. How hard are the small problems that we typically test with numerically, and some of the other heuristics that you need to be able to do efficiently in order to use them without cheating, without solving the problem first. That's what's coming. But today, let's think about computing. We take it for granted, right? Computers are everywhere. So, you know, in your toaster, in your phone, in space, in satellites, in medical devices, self-driving cars. Our world would be completely different without all of these computers. And then there are more unusual computing devices people are playing with. So I've picked out several far from the standard ones here. People interfacing rat neurons, so biological computing devices with silicon chips, people using slime mold to compute, and people actually using test tubes with DNA to do computation. This is just showing you a possible way to encode binary digits into DNA. So what makes them all computers? What is it they've got in common? It's not really useful to say that everything computes, because otherwise that's an empty statement. It doesn't make sense to say something is computing if you can't also say, and then that thing over there is not computing. Otherwise, it's, as I say, there's no meaning in it. There's no use in the statement. So this question, we started out with being a physicist by background. When is a physical system actually computing? And to be a bit more precise in asking what computing is in this physical setting, we've got an abstract calculation or computation we want to do, and we actually instantiate it on a physical computer so we can get it to calculate something that's too hard to do analytically, typically. So we need to relate our abstract model, our abstract computation, to physical objects. And it's a little easier to see what's going on if we start on this the other way around and ask, what is science? Because there, we're representing our physical system as an abstract model. But here we're interested in developing the model and making it relate to the physical system well, rather than just using a computer to do some of our computation for us. And I'll just note now that this abstract physical sounds very much like it's a dualist theory. It's not, and as I come a few slides later, you will see that it's not, but there are consequences to being able to talk about abstract models and physical objects, even in a non-dualist setting. So in order to do this, relate the abstract and physical in the way I've set this up, let's think about how we would do this in science. We have something physical like an electron, and we go on to represent it. We're going to do quantum mechanics here, so we want a wave function for it. And there's Schrodinger's equation and some suitable Hamiltonian to represent the energy and dynamics of the electron, depending on its situation. And now in order to relate these two, philosophers use something they call the representation relation. And it's not like a normal mathematical relation because it is standing for how we relate our models to physical objects. So I'm going to do it with these double arrows, and it will be crossing this abstract physical boundary. And as I said, I'll deal with this apparent dualism later. So the first paper where we set all this up is here. It's open access in Croc-Soke. I've got the references on a later slide too. So the first thing to note, R is theory dependent. So this representation relation, there's more than one way to represent an electron. If we're doing electrostatics, we can just represent our electron as a point charge. And that's all we need in order to do all our electrostatics calculation. So it's still the same physical electron, but depending on what we want to do or what we want to model, we have different models, different theories that we're working with here. So that's why this representation relation has a subscript T. You have to specify which theory you're using in order to map the physical object to whichever model you're using. You can do a diagram of what it's in some sense a cartoon picture, but in another sense it's a way to precisely represent the concepts that we're using here. So what we're doing when we do science, we have a physical object. We've got our model of the physical object. The physical object does its thing, and some dynamics happens over time. And this P primed, it's now in a different state. Something has changed. And up here, we have our model of that dynamics. So we can take our model here, we can apply the model of what's happening over time, and out will come a model, the way the physical object is after that time. But what we can also do is use our representation relation again and observe this physical object in its new state. And so then we'll get a model, outcome of our observations of P primed dash here. So notice the dashes are in different places. In one case, we've calculated what we think we get. In the other case, we've had a look and said, what have we actually got? Now, in general, they won't be exactly the same. It's a good theory and a good model. The difference is going to be relatively small. The key points here is the physical system evolves. The theory calculates that evolution. And if we've got a good theory, it'll agree with our observations to within some epsilon. That is small by some measure of however it is we're observing and quantifying our model. But for science, a good theory has a small enough epsilon. This is a necessary but not sufficient condition. This is not meant to be a complete description of how we do science, just a framework in which you can start to talk about the different pieces that are required. But notice if epsilon is too large, if our theory didn't match what we observed well enough, what we do is we improve our theory. So in science, the reality, the experiments, trumps the theory that we're producing. Also notice that our theory is a model of reality. Models are approximations. They have a domain of validity outside of which the approximations break down and the model no longer works well enough. But if you have a good theory, you can do prediction without needing a reality check, so without needing to actually do the experiment, and you can trust your theory within its domain of validity. So these are commuting diagrams. You can draw commuting diagrams for many, many things. And what we've got are commuting diagrams to within epsilon here. You'll need many interlocking experiments and diagrams to establish a good theory. That this is not, one diagram doesn't get you there. And one experiment doesn't get you there. Typically, experiments are repeated many times, repeated independently, cross-checked, and that's how you build up trust in your theory. The creativity in this is coming up with good theories. You've got observations, you want to explain them, and you have to figure out how to do this. So here's prediction when you have a good theory. So we've got our approximately equal to within epsilon. We need to do the experiment to create this. If we trust our theory, we can predict the outcome here. And we don't need to actually do this piece to know what we would have got by the end. Prediction is using an abstract theory of a well-characterized physical system to calculate what would happen with its physical dynamics. So we have a feeling about science now. Let's see what we can do with this. So if we've got good theories, we can make things that we designed. So here what we're doing is our input system is now our raw material. Our dynamic process is our engineering, when we turn it into a finished project. But we've designed all this with our model so that we know what we're doing here in order to produce the object that we want. And we have a theory we trust well enough so that we expect the outcome to be the thing we designed. So effectively, this inverts the representation relation, so we get an instantiation relation. So this is not a symmetric relation. All that science had to happen before we could make something to order. So they look like inverses, but you have to remember it's not a symmetric inverse in the way that you often think of. So in the same spirit as we looked at science, technology, a well-made widget has a small enough epsilon. And if epsilon is too large, if our widget comes out a bit wonky, we have to fix the widget. So the design spec, the theory, trumps the physical object in technology. But notice that widgets also have normal operating conditions. If you use them outside their normal conditions, you might break the widget. And a good design allows use of the widget without needing to test it within its normal use. You can see that technology is built on science. You have to trust the theory well enough to use it for engineering. And the creativity now is in designing how to use the science. So there's certainly creativity in both areas here. And among many things we engineer computers. And they have a specific type of task to do. We have a problem calculation here that we want to do. But to start with is completely unrelated to our model or our physical computer. So we have to encode it first in a way that the computer understands. Then we can take that encoding, prepare our physical system, which is our computer, let it run the program. We now observe what comes out. And because that's highly engineered and we trust our engineering, we trust that what comes out is going to relate to the theory that designed the computer. We can decode it, and what we get out, unrelated to this, but is now going to be the desired solution to our problem. You see that in an important sense, computing is a high-level process, right? There's two sorts of abstractions before you get to the physical computer. There's a few things we can say immediately that are quite useful. Computations have outputs, or else we could replace the computer with a brick that did nothing, right? So some kind of change or dynamics needs to happen, however that's set up. And there needs to there is involved in computation a representational entity that owns the computation, that owns the problem that they're using the computer to solve. And this is why I'm saying it's not a dualist theory, because this whole abstract here is instantiated in the representational entity, which is a complex enough entity, like us, but it doesn't need to be human, in order that it can process a model and want to do a computation. So just as science and engineering are done by someone or something, physical computing needs an entity doing the computation. And as I said, it doesn't need to be human, it could be biological, it could even be artificial intelligence. You can nest these things. So one computer can use another computer or even use humans to do tasks. So the representational entity, as I said, it supports a physical instantiation of whatever is above that line in the abstract realm of the diagrams. Might be neurons firing, it might be chemical transmitters in a bacteria, it might be electronic memory states. And the science, engineering, computation is meaningful in some sense for the entity. It's useful to do a comparison with communications here. So as physicists or computer scientists, we mostly discussed information capacity of channels, etc. But we nearly always refer to Alice and Bob to acknowledge that actual information being sent means something to someone or some entity. And if we draw a diagram that models the representational entity as well, you get a cube commuting diagram. So the diagram I drew in the first place is this one here. So there's the model. There's the encode coming from the representational entity. And it goes into the computer. The computation happens. There's a change of state. We observe what comes out and decode. And so this is our model of the physical representational entity is down here. And this is our model of the physical representational entity. And the change of state in the representational entity is from posing the problem to obtaining the solution using the computer here. So there's a whole paper explaining all those diagrams. And if you wanted to model us modeling the representational entity, you get a hypercube, but I'm not going to go there in this talk. This is just to show you that you can consistently work this out to the point where it's definitely not dualist. The abstract is instantiated somewhere, and you can model that too. So as I promised, a slide full of papers on this stuff. So that's a nice, if you like, simple theory of what it means to make a physical computer and use it to do a computation. Nothing quantum about that specifically yet. Just understanding what computation is, or a view of it. There are other views, but this is the one that, as a physicist and someone working on quantum computing, that meshes best with the way I view things. So do we have, I'll just pause for a second there. Has anybody got questions at this stage they'd like to ask? Have I bamboozled you completely, or is this making some kind of sense? Silence as...
Okay, I think you can continue.
Yes, good. I'm going to take silence as either complete bamboozlement or everybody's happy. Back to that diagram of a computer. Let's get quantum now. So here's our diagram. We have our problem. We encode. We're still working out how to use our computer. Then we have our physical computer. We run it. We observe the output. We decode it, and we can now relate the output to our original problem. So now if I do a quantum version, you can see basically this is the same diagram. I flattened it out. So I've taken this and I've dropped the abstract physical part of the diagram and distinction, and I put it all in one line. So input is our problem, if you like, whatever it is that we want to solve. We have to encode it if we want to put it into our quantum computers. So this is going to be a quantum computer because here I've got a wave function for the initial state. And it's quantum, so I'm going to have some unitary processing, or I could have an open system, but that would just evolve. I could enlarge the state space and include the environment too if I want in the model. Then I'm going to have an output state. So this, you will have done something to this. And then the same thing, I measure it, I get some output, I have to decode it so that I can relate it to the original problem that I want to solve. This U for my quantum computer, it could be a sequence of quantum gates, or we can engineer a Hamiltonian such that the output is the time evolution of the Hamiltonian applied to the input. This picture, it covers most of quantum information processing. If you're doing communications, your aim is to get the result equal to the input because you want to send the message without corruption. And so there's just one more point I want to make out of this general model. You can see it neatly matches the general picture I gave of computing. And that's this encoding step here. Encoding implies there are some arbitrary choices involved, and not completely arbitrary, obviously. You have to have a system that's big enough with enough degrees of freedom that it can represent all the data you want to put in at the start. But if I'm using spin down to represent 0 instead of spin up, in principle, that should make no difference, provided the encode and the decode are done consistently. Now, in real physical systems, spin down and spin up usually have different energy, and so the errors affect them differently. So that depends how good your model is and how good you are at compensating for the errors. But assuming perfect, it doesn't matter which one you label state you label 0 and which state you label 1. You flip them and it's just a gauge transformation, coordinate transformation, whichever. And that's actually a sign that information is processing is being done. And in the paper on bacteria computing, so we go back here, this one, we identified different signaling molecules being used for the same function in different bacteria. In other words, the signaling molecules were arbitrary, and the bacterium had chosen through evolution what to use that signaling molecule for. Quantum information processing, this is a good way for mathematicians and computer scientists to think about it. It's built on the idea that quantum logic and classical logic are different. There are lots of different logics. I'm not a logician, so I'm not going to give you lots of logic symbols for this. But the idea is that because quantum logic is different, there are certain situations in which it can allow greater efficiency in what it lets you do. So we could make models of lots of different logics, but what's interesting about quantum is that it corresponds to the physical world very nicely, and so we can potentially, at least, actually build these things well enough to compute with them. So that's what makes this one special, is that we think it's physically possible to build these things. Otherwise, we could make models of computing with many different sorts of logic, and that is indeed a nice problem. And using kinds of logic with various types of infinities in them give you fantastically powerful computational devices. But as far as we know, that's all maths, and we don't get to build those things and use them. So quantum gives us different computation from classical just because, if you like, the logic is different. The question then is how different? There are two basic ways to think about what's different. One is computability. What is it possible to compute? And the other is complexity, which is how efficiently you can compute a particular problem. So generally speaking, it's considered that quantum computability is the same as classical. So it doesn't give us magic powers to compute things that are impossible classically. However, the complexity does differ, and some problems can be computed more efficiently. So now we better think about what efficiency means. And it depends on our definition of efficiency, well, how we get our quantum advantage. So in theory, we're interested in, for efficient, what we want is a polynomial scaling with the size of our system, and the size of our problem. Practice, if we're actually building a quantum computer, what we want is something that gives us answers on human timescales. Regardless of whether theory says it's polynomially scaling, if the age of the universe versus the square root of the age of the universe isn't a very useful distinction. So roughly speaking, what we get out of quantum is we tend to get polynomial or quadratic speedups that are exploiting quantum coherence and interference effects, exponential speedups that exploit the parallelism in the quantum superposition. And obviously both are in play in both settings. It's just a question of whether the particular problem we're applying them to lets us exploit them. We then, of a real physical computer, isn't dependent on complexity theory alone. That will tell you what's possible in a scaling sense, but in practice, you have other criteria you're going to need to meet. So that's very much my physicist who would like to have a real quantum computer view on things. But it's useful to remember that efficiency isn't just one concept here. It depends what the purpose is that you're asking the question for. If I'm going to be interested in whether they're useful in practice to actually compute things with, we better go back and think about our current computers. So if a quantum computer is going to be useful, it's going to need to be better than what we currently have or are likely to build in the near future. We have plenty of computational power, it seems, our phones and laptops. We can afford to waste our compute power, if you like, on fancy graphics and computer games. We certainly didn't used to have all of that. And our batteries, they're rechargeable. We can schedule the charging to use renewable resources. So maybe they can even help to balance the load on electricity grids. Still need to think of repair and recycle for the resources they're using. But then there's the ones that you don't see, because your smartphone wouldn't be very useful without the internet. And network devices need big computers to provide the services, and they're on 24/7. They use 50% more electricity than the devices, and they use about 4% of global electricity in 2020. That's a lot of resources in a world full of climate change and global warming. And if you include all the TV and other network devices and streaming, you get to 6% of our global electricity use is on phones and smart internet connected devices. So I'll just leave that one there for a minute. About where quantum computers might be useful. We need to think about really big computers, because up to a point, we can just use more small computers. Quantum doesn't necessarily help us with that. So really big computers where you have to have a whole set working together in order to do the computation. They're doing things like simulating biomolecules, molecular dynamics. They're modeling pandemics. They were modeling pandemics well before the COVID pandemic. They simulate the human body, design new quantum materials. A big use is weather and climate forecasting. And you need that in real time, right? It's no good having tomorrow's forecast next week. It's too late. You need it before tomorrow for it to be useful. Nuclear explosions, and there's a whole bunch of other defense and security and military uses that they don't tell us about. So who has them? So this is a diagram from, I could update it for the most recent one, and it will be June 2022. I probably just forgot to put the link in. I think I've already downloaded it. But what this does is it makes nice pictures where you get a sense of where resources are, if you like. So if I squint enough, this is the United States, which has more than anybody else. This is Japan, which has the fastest, the biggest supercomputer. This is China, which also appears in the top 10 list here, with 2 of them, these 2. There's Germany. That one is also in the list at Jülich. I think I'm trying to pick Canada out here. That's the UK. That's France. And that one maybe Canada? There. Yeah. So these are these computers where they have the biggest total compute power in one multi-core machine. So kind of like banks and warehouses full like this. So there are 2 ways you end up with very big computations. One, the problem is efficiently described, but the memory and time you need to actually compute it is enormous. So weather forecasting and simulating biomolecules come into that kind of setting. The other way is that you have an enormous amount of data, but the computation goal, the output, is quite efficiently described. So training AI, for example, or finding Higgs boson signals in CERN data, or finding interesting signals in data from telescopes for observational astronomy, for example. The other thing to realize is that computational scientists are always dreaming bigger, usually by several orders of magnitude than currently available hardware. And past experience tells us that if you've got more efficient computing, what will happen is more computing will get done, not that we'll save energy. So if we need to curb our computing power, we will need some different routes to do this. So if our goal is to increase computing power by using quantum, for example, we have to note that current computers are already very powerful. But they're not getting that much more powerful because silicon chip technology has more or less reached its limits in terms of delivering more compute power. It's still developing, but it's not making faster computers. And the other limit is energy consumption is very far from optimal. And we are reaching resource limits. And in terms of how much energy we can make electricity for computing. There are projects to do lower powered silicon, for example. So what happened to silicon chips? We had this exponential scaling. We basically got more computing power because they made smaller and faster transistors on the chips. And that went on till about around here, somewhere around 2010. It used to be that everybody would put Moore's law graphs up. This one is from about 2000, and it's naming all the chips here. So this is the piece of the graph up to about here. Then I went looking to update it, and I couldn't find any more graphs like that. So I downloaded the Intel data from their website, from their historical description of chips, and I plotted this myself. And then I ran out of time and energy to plot this bit, because they now make hundreds of different types of chips. So this is the speed in hertz, and it's leveled off. They're still making smaller features. The only way to get more performance out of the chips is to make a chip adapted to every given application. So you can buy chips that are ideal for mobile phones, you can buy chips that are ideal for laptops or for desktops, or for putting in space because they're much more rugged, or for sending down a mine because they'll work in a hotter or a damper atmosphere than normal. And the ones that don't pass the tests but still have some compute capability, they get put in the toasters and the other devices, all of which have some sort of display with a silicon chip behind it somewhere. So what's happening to computing is it's diversifying, it's optimizing for applications, because we can't just continue this 50-year run that we had of just making them faster by engineering them to be faster. And people are looking much more seriously at what comes beyond silicon. So there's the crazy 3 I put up. There's another crazy one doing reactions in liquid and chemicals. There's one of IBM's early computer chips. This is a reservoir computer. It's this particular instantiation. Reservoir computers are a theoretical model. This is a blob of resin full of carbon nanotubes, and then a whole bunch of electrodes in there. So you've got a random network inside here that is doing the computing. So it's not quantum, but it's nonlinear, highly nonlinear, and that can make for a powerful computing device. Hybrid computers. In practice, computers are full of co-processors. Conventional ones, we've had graphics cards for 20 or more years, but they're now the high-performance computing, so there's really big computers are also having banks of GPUs, banks of FPGAs that you can use for specific repeated intensive computations. And all of the unconventional ones that I was talking about are essentially a substrate and a conventional computer used as a control. So they're hybrid, however you look at it. They're the norm in practice. You look at what we have for theory, and we have single paradigm theories. So we have a Turing machine model for classical computing. We have Shannon's GPAC for analog. We have a bunch of different quantum models, which I'm not going to be part of this course. I'll mention there's quantum walk and adiabatic, which will both get a mention. There's intermediate ones like linear optics. Missing is how you put these together. If you like a little bit of summary of what I've just been telling you. First of all, we asked what computing is, and I've described it as a high-level process that needs representational entities, and gave you a nice diagrammatic way of thinking about what we do when we do computing or science or technology. The concept of efficiency is an important one to remember. The model may be efficient, but that's not the same as saying the physical computer is efficient in producing a useful answer on a relevant timescale. Then, in the sense, the important open question is, hybrid is what we normally build in practice, but the theory is very underdeveloped. So this is a complete aside, but there's a whole volume of Phil Transroy-Soke, which is open access. And heterotic computing is the idea that when you put two different types of computing together, you gain an extra advantage. The whole is more than the sum of the parts. And so there's a whole volume of papers about that, about the concept. So as you can see, this is a really exciting time to developing any sort of computing, whether you're doing bits of theory related to it, or whether you're trying to build hardware, because there are changes happening across the board. It's not just that quantum is new and exciting and shiny, but computing as a whole is needing to evolve beyond the norm that we've had for the past 50 years. So this is why I work on the stuff, computing, quantum and otherwise, but also hopefully inspiring that even in a corner looking at the theory of it, there are lots of contributions to make to what we might have in future in the way of computers. Today's lecture with the overview again. So I've just done a what is computing discussion with some nice diagrams. And tomorrow I will talk about how we might use quantum walks for computing, now that we've got all the context for what we mean by using a quantum walk to compute. Very much. I will wrap up there, not to throw too much at you in one go. I'm very happy to take lots of questions.
Question here or online?
Well, thank you for the very nice talk. It was, I think, part philosophical, which is really great, because I think philosophy has to do with it. And actually, the last talk where I went about quantum was a philosophy, the last conference was a philosophy conference. So there is a lot of philosophical aspect. I just want to just comment on a very small part where, so you talked about complexity theory and the role of complexity theory in the big scheme of things. And I completely agree with you that complexity theory, some people take it too literally. But I always tell to my students that in the complexity theory, like when you say that this algorithm is exponential or polynomial or n log n, that just gives an additional piece of information about the problem, or just additional intuition, just adds the general intuition and the other components that that play a role could be computer experiments or understanding the problem in other ways. So one should always take complexity theory with a grain of salt. And I think that's that's well known, or the complexity theorists at least know that it's just a story. So basically, complexity theory is just a story, which is a helpful story, but it's not the whole story. And I completely agree with you that, like, when we say that, okay, we can do this and this in quantum polynomial time, then it does not necessarily mean that we can really do it with quantum polynomial time, because the quantum polynomial time is so unexplored that with all the error correction and complicated things that go on, the lack of good devices, that it's really a question whether quantum polynomial time is really a good indication.
Thank you for your comments.
Thank you. And I was very careful how I phrased it. It's important. Complexity theory gives you an indication, and it's certainly good for relative. It can be very good to tell you relatively how hard things are. Sometimes an exponentially hard problem is so important that you need to solve the biggest one you can anyway. So it's what's useful in practice is not necessarily, it will tell you it's going to cost you, but it won't tell you how much.
Yeah, and sometimes it's the opposite. Like sometimes polynomial time and it's still very costly, and sometimes it's theoretically it's exponential time and still you can do it. So it gives some kind of information. Just I would say it's an additional information to many other informations when you study a problem. So and then I think the complexity series, at least I am modest about it. Like I don't say that, oh, this is polynomial time, so it's easy, and this is exponential time, it's hard.
I think a lot of what comes out of it also that's really useful is understanding how different problems relate to each other. So understanding what different types of problems and how you solve them, that certainly is an important part of complexity theory. It's not just about proving a scaling, but it's about understanding what the characteristics of a problem are, and different ways in which different problems are similar or can be mapped to each other. That's also very, very valuable.
Yeah, I completely agree. Like, for instance, if something can be solved with linear programming or dynamic programming, so just to understand the nature of the typical algorithms that can tackle a problem, that's already very useful. All this information, so all of the above, I think one should consider all this information. And indeed, if some problem reduces to another, yeah.
Any other comment or yes, please.
So you thanks for your talk. So you mentioned energy consumption, and there seemed to be some hint that you see us as finding ways to reduce energy consumption, but then you also have this comment that we're sort of addicted to bigger computing, and that any more efficient way of computing is just going to make us use up more energy. Is there a punchline to this line of reasoning that you presented?
Very much a watch this space, because so again, I could go on putting more about any topic into a talk, and I don't want to diverge too far. But if you've been to a high-performance computing center, they've probably also shown you the power supply for those computers in megawatts, and megawatts is enough to power a small town. And the cooling that they now need, because there's so much waste heat from all of these computers, that they're usually water cooled by now, and then they need to find a use for this waste heat. So it becomes district heating, or it's fed into other industrial processes. If you look at that, if you want another order of magnitude of computing power, never mind the 3 that they're going for now, you can't scale that up to 10 or 100 or 1,000 times anymore. So you're going to have to reduce energy use no matter what you do. So there's a turning point happening for that reason, on top of everything else. So the level of engineering that's going on to change the power consumption of classical computer hardware is really quite significant now, because we won't get faster computers unless they do that. It's kind of the only route at this point. So there isn't so much a conclusion in a sense, because this is an ongoing process in Europe, in the US, in the UK, in any of those places that have a significantly large one of these blocks, wants to build the next generation. And in order to do that, they need to find hardware that is going to not use 10, 100, 1,000 times more energy, because we simply do not have it. Now, whether quantum can provide a reduction in energy use for faster computing power is very, very hardware dependent. So we went a couple of weeks ago, I was on a little tour of one of Durham's high performance computing facilities. In fact, it's one of the ones that does the particle physics calculations and cosmology. So it's not by no means the largest in the UK, but it was impressive enough to see. One of the experimentalists who does superconducting experiment, he looked at this space and went, what's the power use in here? Was told, of order of megawatts. And he went, right, that's about 30 dilution refrigerators, each of which could contain a quantum processor. And yeah, the floor area is about comparable. So right now, what you could do with 30 of, say, IBM's best current chips, or D-Wave's current chips, could you tie them together? Answer no at this point, because we have not developed the interconnects well enough. But we're going to need to get the engineering to reduce the power consumption of the quantum processes as they develop as well. Because right now, dilution refrigerators are power hungry, and that's what most quantum processes need to be put in. So it's very much an experimental question, and it's what they manage to do as they head into the future. So not really the topic for a mathematics workshop, but worth thinking about as a backdrop.
Any other question, comment? So let's thank again, Dave. We'll wait for you at 1:30 for the next mini course.